So what this is called ICND2Review1. It's a review of Monday, Tuesday, the topics that we talked about. We'll go through them hopefully relatively quickly here. So the lesson one was VLANs, again, virtual local area networks. And what they did, and I think we created smaller logical networks, smaller broadcast domains is what we did. We had the different IP subnets. We could have had different switches with them on it, and what we saw was if we had machines on different switches, we'll go in here and I'll get a white. Let me get a white ink here. It works a little bit better on this color, I think. If we had different switches here with machines attached to it, when we connected the two switches together, if these guys were all in VLAN 1 and this switch was in VLAN 1, they could talk to each other. When we put them on VLAN 5, for instance, and 5, for instance, just for them, and this was still on 1, they couldn't talk to each other. That's why we needed the trunk ports. The trunk port allowed us to have all of the VLANs on it, and we saw that we could control access to those VLANs. What we create with them with a VLAN 1, or not 1, but let's go 2, 3, 4, and 5 is we're going to create broadcast domains. So as we create them, we create more broadcast domains. We don't have any impact on collision domains. And in the switch itself, each of the individual ports becomes or was a collision domain anyway. So we have multiple collision domains already on a switch. That's what it did for us. And we had the VLAN ranges 1 to 1005, I think, was the normal, and then we could go up to 4096 for extended. 1 and 1002 to 1005 were VLANs that were pre-configured by Cisco. We can't do anything about them. So if we want to create them, the numbers that we can use are 2 to 1001. We had private VLANs, and in the private VLANs we had the isolated, community, and then we had the promiscuous VLAN, or the promiscuous interface, basically. Isolated could talk only to a promiscuous interface. So what that really did when we did the isolated was force us to use the router to get from one location to the other. In the community, we could have a number of machines in the community that could talk to each other, but if they wanted to talk to any of the other machines, communicate with any of the machines outside of the community, they had to go through the promiscuous port. And the promiscuous port should be on the router, so that it would then allow us, or the promiscuous VLAN on the router, and it really winds up being a port on the router, so that it can talk to the isolated, allows isolators to talk to isolated through routing, and promiscuous or communities to talk to other communities. The reason we go through the router is we can have our favorites there, access control lists on it, and control who can get to where on these things. So, and then we talked about access ports. We had the MDI, MDIX, which was an automatic, whatever type cable you plugged in, it made the port so that it was the correct cable. What this does is eliminates the need for crossover cables. And the access ports, 1 VLAN. Access port 1 per VLAN, unless we have a voice. We had the voice port, we have voice VLAN, and we talked about how that worked if we had the switch here, and we had our phone down here and our computer plugged into the phone. I still can't draw computers, as you know. And then the phone plugged into the switch here. The phone would assign the voice VLAN ID, the voice VLAN, and it would treat the data port here as a native VLAN, as a native port, and not tag it, so it became untagged. When the data got to the switch tagged it with the VLAN number that the data VLAN was on. So the voice, how do we get 2 on an access port? That's the way you do that. And what all the answers are going to be is an access port has 1 VLAN on it. And they may say, well, what happens if you have a voice port? If you have a voice port, you can have 2. And the trunk ports, which I didn't put in the typing there, the trunk ports can have all the VLANs. And we can control which ones are on it. Default VLAN is 1. We can't do anything with it. We can take the ports off of them and put them on other VLANs, which we have done. The native VLAN we can control with the switch port native and then VLAN number to change it. We need to have a match. We need to match the native VLANs on each switch on both sides of the trunk, and the native VLAN is a trunk thing, because that's the only time it makes any difference. The native VLAN is the one when it goes into the trunk port, says, you're coming from the native VLAN, I'm not going to tag you. And when it gets to the other side, it says, okay, you don't have a tag on, you go to the native VLAN, whatever it is. We want to match the native VLANs on both sides. If we don't, if we had a 3 here and a 5 here, native VLAN untagged is on 3, goes into the port, goes into the trunk, no tag, comes out the other end, goes to VLAN 5. So we have that VLAN, what was it? VLAN leaking, they called it, and some people call that VLAN what is it, hopping. We can do those things. More in the VLAN, we had the trunking protocols, which were ISL, Cisco proprietary 26-byte header. .1Q is the standard that we use on those. .1Q uses a shim inside of the it goes in the middle of the frame, so that we have .1Q is a shim that is put in when it goes into the trunk, taken out when it gets to the other side, and then sent to the proper VLAN, whatever it is. We had the dynamic trunking protocol, and that's what this this thing is here. Are we going to create a trunk? Dynamic auto is the default. So dynamic auto is the default on the new switches. On the old switches, legacy switches we'll call them, on the old switches, dynamic desirable was the default, which is a dangerous thing, because dynamic desirable, if we plug anything into that port, it's going to automatically negotiate that port as a trunk port if it's in dynamic mode. So dynamic auto, will it form a trunk? If it's in dynamic auto, both of them are in, both ends are dynamic auto, it's going to remain an access, and of course the white won't draw there. Dynamic desirable, it's going to be a trunk. If we use the switch port mode trunk command, it's going to be a trunk port. Switch port mode access, it will be an access port. Dynamic desirable, we're going to create a trunk with everything except the access trunk, because it won't negotiate. If we switch port mode access, it's not going to obviously, because it says don't be a trunk, be an access port. If we do switch port mode trunk, static trunking, we have a trunk except when we get a trunk on one side and an access on the other, limited connectivity. Access, switch port mode access, it's going to be an access with all of the dynamic protocols, but with the static trunk, limited access again. VLAN trunking protocol, VTP, it was the thing that we could do. We could create the VLANs on one switch, on the servers, and on the transparents, and on the server, it sent it across the domain. We had to configure a domain on here. It didn't matter what it was. And the domain shared the VLAN information with all of the switches that were in that domain. So we have a domain, we have clients and servers, and we create a domain on a server switch, and as you saw when we tried to, you can't create domains on client switches. But we create it on the server, it sends it to all the switches in that domain so that we don't have to go to our 37 switches and create the domains. We do have to go to our 37 switches and put ports in those VLANs. A transparent switch, we could create them on, but it didn't share that information with anybody. So a transparent switch creates VLANs for itself, only for itself. If it's in the topology and we create one, the server sends it to the transparent will relay it to the client machines and to the other server machines. So we can only create them on servers. Clients receive that information. The next one was spanning tree, and I'm sure that you heard more about spanning tree than you ever wanted to know. But the spanning tree is a protocol, and it's designed to prevent network loops so that we can have something like this, and then we'll have one of these guys, and let's see if we can pick the correct one. This is going to be the lowest. One of these guys in blocking mode, so that in case something happens over here in this link, for instance, we have a secondary path to the root bridge. And the root bridge, you remember, goes through an election process. We had a priority that we could manage, and we put the priority with the MAC address. We got the bridge ID, the bridge ID. The one with the lowest bridge ID becomes the root. And if you look at these here, all zeros and then a zero, we don't have to go very far to say, okay, this has got they're all 32.768, the default. Don't have to go very far to say, yep, this is the lowest, it's going to be the root bridge. Then we're going to calculate the cost to get to the root bridge. After we find the best path for each of the devices to the root bridge, we'll figure out which of the ports is going to be blocked. The default issue is the lowest MAC address is probably going to be the oldest switch, which will be the least capable switch. The port roles, we have root ports, and the root port is the one that connects to a forwarding port, and the forwarding ports, each of them is going to have a forwarding port, but root port is the direction it's going to get to the root bridge. The protocols, .1d is spanning tree per VLAN spanning tree actually. Rapid was 802.1w, and multiple spanning tree was 802.1s. Per VLAN, and when we talk about spanning tree now, we're talking about per VLAN spanning tree plus, which is Cisco, and it runs with .1q. Spanning tree, the original spanning tree was an ISL. Root bridge is elected, and it's going to be the one with the lowest bid. We can impact this priority here, 32.768. We can manage it. So if we wanted a bridge or a switch to be the root bridge, we just make this a really low number. And in the configuration, there is one that said you can make this a root, and it'll automatically set it to a priority that's lower than everything else in the system. The port states in spanning tree, we see here we had blocking, and in the per VLAN or the spanning tree here, the regular one, the default one, per VLAN spanning tree, we're in blocking for 2 times the hello time, 20 seconds, listening 15 seconds, learning 15 seconds, and then we could go into forwarding state. Rapid per VLAN spanning tree, RSTP, and it is spanning tree is configured on a per switch, or actually a per VLAN basis, not on ports. So we cannot configure rapid on one port and regular on another port or whatever else. It is a VLAN based protocol. That's why it's a per VLAN spanning tree PSTP, although we just call it STP, and a PRSTP, per VLAN rapid spanning tree protocol. What we do with rapid spanning tree, it goes from 10 times the hello time to 3 times the hello time, so a maximum of 6 seconds before it moves into the learning state. So the discarding state, which is in the blocking and listening in the per VLAN, this is you want to talk about tongue-tied, is the equivalent of the discarding state. Combine those two in the rapid per VLAN. And then we go into learning state for 15 seconds. So we're talking, what, 21 seconds versus 50 seconds to get there. Port fast is something that we can configure on our access ports, which doesn't do spanning tree protocol. It says don't worry about it. This is an end device. It can't possibly create a loop. And when we do that, the ports come up immediately. When we configure port fast, what happens if somebody plugs a switch into it? That's where BPDU guard comes in. If we have a port fast port and we assign BPDU guard to it, then somebody plugs a switch port or a switch into it, and it receives a BPDU, a bridge protocol data unit, and only spanning tree does those. I digress. Then it will go into error disable mode, shut itself down. Edge ports, and I talk about topology changes. One of the reasons to have, a big reason to have an edge port is so that when it comes up and down, a computer comes online, we don't send topology changes. So spanning tree doesn't have to go work its magic and recalculate the topology. We have switches come up and come down, it's going to recalculate the topology. So edge ports, no, okay, something changed, now go figure it out. A switch up and down, yeah, it does that. An edge port gets to be an edge port by making it an access port and then configure it with port fast. So the edge ports are the ones that are going to have the devices into it. And then we went to lesson 3, which was entitled Aether Channel, but started out with switch stacking. And a switch stack could have 9 switches in it. It provided a single point of management, availability, and redundancy. And remember, in that, the redundancy, high availability and redundancy, was because we had a counter-rotating ring in the specially configured ports on the back of it. To allow us to connect these things together to appear on the network as a single device. And that's what gives us the single point of management. We send the configuration changes to the stack master, which is elected, and if everything is the same, it's going to be the one again with the lowest MAC address. If in a guessing situation, high or low, and it's a switch, the guess would be that it is the lowest whatever. That's what they tend to use. Well, when we get into routers, it's going to be the highest whatever. So we had the stack master, everything else going to be a stack member. If the stack master, something happens to the stack master, they elect a new master in order to do that. The stack could be homogeneous, which would be the same feature set on the iOS and the same router or switch types, the same switch types, 3750, all 3750s, all 3750Zs. The mixed stack, we had 3 types, 3 mixed stack types. It could be a mixed hardware, different types of hardwares in it. Circle the 3 here. So we have mixed hardware, mixed software, or we could have a hardware-software configuration. Mixed hardware, we could have 3750s, 3750X. I think these are the right number. Mixed software, different iOS versions maybe. Or we could have a combination 3750, 3750X, and different feature sets in the iOSs. So they would be different iOSs. 3 different ways to have a mixed stack in the switch stack. Aether Channel itself was the ability to aggregate links. We took a switch and we could take several ports and combine it to make it appear as a single entity. So if we had three 100, we say these are 100, three separate 100 meg ports that we put together, we would have a 300 meg port, and we used what channel group in order to create these things, and the interface became a port channel, interface PO1 or whatever we named it. We named these things. We could have what I think up to 8 of these to aggregate. Two different protocols, PAGP and LACP. PAGP is Cisco proprietary. LACP is a standard, IEEE standard that we used here. Will it form an Ether channel? And we could also have on, which, as we saw, is really not recommended by most people because of the possibility of creating loops with these things. So in LACP, we have active and passive as the two options when we configure the mode. If we have an active and active, we will form an Ether channel, an active and a passive. Passive and active obviously will. Passive and passive will not do that. We can't mix these two. We can't have an active and then a desirable. In the PAGP, desirable and auto, and those were I think the same terms that we used in the dynamic trunking protocol for switches. So a desirable and a desirable will form a link. A desirable and an auto will form a link. Auto desirable obviously, and auto will not. If we do on, both ends have to be on. Unlike in dynamic trunking, where if we did a switch port mode trunk and it was auto, it would negotiate. That doesn't happen here. If you do that, if you want to do the statics, you have to do the mode is on and mode is on both sides of the Ether channel, both sides of the trunk for the Ether channel, both sides of the access. Then we'll say trunk, both switches. Same configuration, we have to have the same speed, same duplex. If we're doing a trunk, they all have to have the same VLANs allowed. Same allowed VLANs on a trunk port. So the configurations have to be the same for it to form an Ether channel. Then we managing threats to the access layer. This is where we talked about, and we already talked about this a little bit earlier, the native VLAN needs to be the same on both sides. Otherwise, we get the VLAN leaking where we go from what we did 3 to 5. If this one's 3 and this one's 5, we start out untagged on 3, go here, we wind up on 5. We will get, and hopefully you saw in the lab, you'll get an error message that says that you have a native VLAN mismatch. Native VLAN mismatch, and it keeps coming. It will tell you which ports have which native VLAN on it, so you can see what the VLANs are that are configured as natives. The allowed VLANs on the trunk is another way to control threats. Which VLANs do we want to allow on the trunk? And the native VLAN, what many people recommend is that you send it out someplace like 999 and don't put any ports on it. This still allows the control traffic to go across the trunk to the devices. But we don't have any ports on it. We don't really have the possibility of doing the VLAN linking. And then we had AAA. We had the AAA new model. No, I didn't do the end here. And the AAA authentication, authorization, and accounting. Authentication, who are you, who you are, who you are. Authorization, what can you do? What can you do? And accounting, what did you do? What did you do in these things? And we could also have, what the radius, to have it RADIUS, okay, messy, I'm sorry. Radius, TACAX, which could have accounting on them. And then we had the local database where we made usernames and passwords, and this one had no accounting. So the local database could do AA, authentication and authorization, and we did this with our authorization level, the word that I can have a lot of trouble remember, but we can go 0 to 15, 15 being root, and 0 being like user. And then anywhere in between here, we can create levels and specify commands that can be executed at that level. That's how we get the authorization. The method list, when we did AAA, and which methods and what order are we going to use for authentication? We could have radius TACACS local, radius TACACS local database. We could also have had enable, and we could have had none. What happens is it goes to the first one in the list. If the radius is available and you just don't know username and password, it locks you out. If it's not available, it goes to the second method. If it's not available, it goes to the third method on down the line. And then back here, the servers have accounting and no accounting on the local database when we get into this. 802.1x is an authentication protocol. We use it for port authentication. When we do it, we have to have a radius server. We had to have a radius server, and we had to have other things configured. It allowed the voice to pass through. It also allowed EAP, the Extensible Authentication Protocol, over LAN packets, frames to pass through so that it could do the negotiation. We could still, CDP could go through, STP could go through prior to authentication, and we could also have voice. We could still have our phone calls would go through. Supplicant Client Authentication Service. Supplicant is the new name for what we have called in the past client. So if we have a computer back here that's trying to get access to a port on a switch, the switch is going to be the client. This guy is going to be the supplicant, and our radius server back here is going to be the authentication server. The authentication server back here. So we have these things. CDP review, we have two commands. We can turn CDP off, and sometimes some people do for security reasons. And if you go to some place and it's on, you need to ask You need to ask permission to turn it on if you need it to do troubleshooting or whatever else. CDP run. I think we enable it. I have to look it up. You need to check this one. No CDP run, and CDP enable. I had this sorted out in my head, and now I don't have it sorted out in my head. I think we enable it on interfaces, and we make it run on routers. Can't get it up here. Anyway, I'll look that up. I'll get back to you on that one. 802.1x, anyhow, we go back to their 802.1x. We had single host and multiple host. The single host was a single machine, obviously, and the multiple host was one logs on. We go back here and we have a bunch of hosts down here. One of these guys authenticates to this port. All of the everybody else in the multiple host can get in there until this one finishes, and then we will not have access to the other. Somebody else has to authenticate to that port. 802.1x and port security, the MAC address lists, we can configure both of them at the same time. 802.1x for authentication, and then port security for access to that port, access to the port to be able to turn the port on. So we can have two different controls on a single port. .1x username and password or whatever we're using to authenticate, and that port security is that device allowed on there. We did have authentication bypass if the server goes down. If we have a client that is not capable, we could use, if we used a MAC bypass and we had a client that was not capable, we could configure it so that it would use its MAC address to get onto it. DHCP snooping was a switch thing with a DHCP server, and this was to prevent rogue DHCP servers. We had computers here that are trying to get DHCP addresses. We can, if we do IP DHCP snooping, it makes all of the ports untrusted, which basically says that the DHCP server can't answer. We have to go into that port and make it a trusted port, so that we're then allowed to use all of our DHCP services. These guys can get addresses. So DHCP snooping is for rogue. I think that's right, to prevent rogue DHCP servers. And we had some stories, and I told one, SRVR. You can shut down a network by having a rogue DHCP server. You get IP addresses and default gateways that take you nowhere, and that's where you go, is nowhere. ICND1, a couple of reviews. Let's say you go in and this is a show IP interface brief. These are up. What can cause these ports to be in an up-down situation? Any guesses on that? What will cause it to be an up-down? And I know a couple of you had it in a couple of the labs. Up-down. What does the first up mean? Mismatches. And the mismatches could be we don't have a clock rate on the DCE. We said we had to have that. Or we had a protocol mismatch. We had maybe HDLC on one and point-to-point protocol on the other one. The first up is the physical connectivity, layer 1 connectivity. So if you go into, and I think that somebody had a serial port that they had configured and brought it up and did this, and it still said down because the other end was down. So we have to have both ends up in order to get an up. And then in the this is gigabits. Typically the gigabit, when you plug them in and you have the correct cable types, or the MDI, MDIX, it will then bring it up, and it's probably going to bring the protocol up because we don't change the Ethernet protocols all that much. Serial protocols are really the ones we have to pay attention to. HDLC is the proprietary on Cisco. If we go to another vendor, then we need to go to the PPP protocol. So the causes there, NAT and PAT. NAT was network address translation. PAT was port address translation, where we use the IP address on the interface along with the overload command after the IP NAT inside source list and all that other stuff. The source list was the access control list of the devices that could get a PAT address, and we use the address on the interface, and we use the IP address and a port number, a socket, to make these things unique. And the last one down there was subnetting, and these are kind of things that they will ask different kinds of questions in different ways. But if we had this 25, which is a class A with 29-bit /29 CIDR notation, 29-bit subnet mask, how many valid hosts are you going to have on the network? Has anybody got any guesses on that one? Calculations. There shouldn't be guesses on that one. It's going to be that you know that, right? How many bits are going to be left for hosts with 29 for the network area? You guys are not being very talkative, are you? 3. And so how many total IP addresses are with 3 bits? 2 to the third is going to be 8, right? And then we have to take out the network address and the broadcast, so the valid hosts are going to be 6. And the other one is, if somebody asks you, this is a 150 is going to be a class B, and we have a /22, how many subnets? And I'll just go ahead and talk through that one. The class B, class full CIDR would be 16. So 16 would be there. 17, 18, 19, 20, 21, 22 would be 6 bits. 2 to the 6th is 2, 4, 8, 16, 32, 64 subnets would be available. We used to have to take the 2 away. You don't have to do that anymore. And the reason that you don't have to do that is if you look into the router configurations, one of the first commands that I think you'll see is subnet 0, which allows the use of subnet 0. If you're doing this for Windows I think you still have to take away the 2 on the subnets. So subnets are just however many they are. If we had the 2, 4, 8, 16, 32, 64, the 6 bits, a 22 bit would be the 64. If we had 23 bits, would be 128. So we just double that each time. And that is the end of my little review here. You have questions about that? I'm going to